was correct. Okay. Draw the Lewis structure for tellurium chloride, and so forth. So I'll go through each one, and then we'll go through the questions that it's asking afterward as well. So first, just the structures. So for tellurium chloride, so this guy has 6 electrons. Each of these contributes 7. So that's 28. So then we've got a total of 34 electrons. So I'm just going to draw the same way I kind of normally would. The only thing is, we need 4 bonding partners, so we might as well make sure that's there. And then a lone pair. And so tellurium is far enough down on the table that it can become hypervalent, so there's not really a concern about having the lone pairs be in any particular orientation. We already know that it can do it, so might as well just set it up to bond how the molecule shows it's bonding. Alright, so there's our bonds to chlorine, and so we've got a single lone pair and four bound species. So that's for 5 connected species, it always has this kind of structure, where this is coming out of the page, and that's the lone pair. And then we got chlorine, 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 chlorine. Alright, so there's our structure. And so this is a seesaw. It also wants the hybridization, so we're going to go through that. So for hybridization, we would always use an SP D notation, where we drop the D if we don't need it. But basically the numbers, where if there is no number, it's a 1, adds up to the number of species bound, and we could only have 3 p orbitals. So in this case we need 5 species, including the lone pair. So 1 plus 3 is 4, so we need at least a single d orbital to give 5. So the hybridization is sp3d. And then the angles in here are going to be, because of the lone pair, we're going to get repulsion, so this is going to be less than 90, and the angle, how do you indicate this? So this angle in here, it normally would be 120, but it's going to be less than 120. Again, because of the lone pair, which is going to be repelling. Okay, so ICl5. So this guy has 7, and then these contribute 7 times 5 is 35, so total is 42. Again, ID normally would have 7, but obviously it has 5 bonding partners, so we're going to need to put those in. And then it'll have a lone pair left over. Alright, I'm making these bonds progressively different sizes, but it's okay. If we count everything up here, right, so there should be 2, 4, 6, 8, so 8, 16, 24, 32, 40, and then 2, so that's our full electron count. This kind of looks like garbage the way I've drawn it, but I'm going to draw the full structure, so I need 6 bound species, so that's going to be our general octahedral shape. And so I'll have the lone pair going up, a chlorine going down, and then the other ones will all be out of the page and into the page. And because of the electron repulsion, everything's going to be pushed down, so this is actually going to be less than 90 and less than 90 here, or actually greater than 90 here. Yeah, because these will be pushed apart as it goes down. So these guys will kind of umbrella down. And iodine in this case has 6 bonding partners, so following the same rules, we need 1 plus 3 plus 2 equals 6, so sp3d2. Okay, PCl5. Phosphorus has 5. Each of these contributes 7 times 5, which is 35, so 40 total. Our phosphorus has 5 bonding partners, so we might as well split all 5 of the electrons. Okay, I'm just going to fix this chlorine. There. Okay, and so we have our 40, 8, 16, 24, 32, 40. It's bound to 5 partners, so we're going to use our generic 5-member structure here, where these are coming out of the page, into the page, straight up. Okay. Then we can put our electrons, our lone pairs on here. All right. Sec. Okay, so this guy's perfectly symmetric now. It's, I suppose I should have been putting the names on there too, but maybe we'll go back through and do the names. But I'll continue with the angles and everything. So these angles are going to be 120, and these angles are going to be 90. Because it's perfectly symmetric. And then for our hybridization, we need 1 plus 3, as that only goes up to 3, so we need 5 total. So 3 plus 1 is 4, plus 1 is 5, so sp3d. Okay, and now I'll do the next one. So krypton chloride. Okay. So krypton has 8. Each of these contributes 7, which is 28 total. So then the total is 36. We already know that the krypton needs 4 bonding partners. and then might as well plunk in the lone pairs just like that. Okay, and then bond them. Okay, that looks good. So we've got 8, 16, 24, 32, and 4 is 36, so that looks good. It's got 8 bond. The krypton has 6 species around it, making it our general octahedral structure. So I'm going to go ahead and put the lone pairs above and below. And then I'm going to put the chlorines in the plane. Like that. And they're lone pairs. And again, the wedges are coming out of the page and the dashes are going into the page. Okay. So these angles in here are going to be 90 degrees. And since we have 6 bonding partners, we will need 1 plus 3 plus 2 to equal 6, so sp3d2. And then for the last one, xenon chloride. So we've got 8 and 2 times 7 is 14. So then in total we have 22 electrons. So our xenon has 8, but obviously needs 2 bonding partners. So then there's our 8 electrons. And there's each of the 7. So we've got 8, 16, and 6 is 22. So we've got 5 partners around xenon. So I'm going to go ahead and plunk these on the equator. Okay, and so our molecular structure is linear, but our xenon is bound to 5 partners, so sp3d, so 1 plus 3 plus, so that's 4 plus 1 is 5, so it's just sp3d hybridized. Right, and the bond angle here is 180. Okay, so now going through these questions now. Which of the compounds exhibits at least one bond angle that is approximately 120 degrees? So I'd say there's the PCl5, definitely. So here we have a bond angle that's 120 degrees. So I'm going to summarize this at the end here. Oops. 120 degrees. So PCl5 was 1. And so these are all about 90. Tellurium chloride would be roughly 120, but a little less because of the lone pair, but I'm going to throw that in the list as well, just because I'd say tellurium chloride are less than 120 degrees, but it's closer than the others. Not that it necessarily needs to have more than one. So which hybridization. sp3d2. So we went through and did that. So so the krypton, the KrCl4 species had that hybridization, and I believe there was another one. The ICl5. And I don't think there was another sp3d, sp3d, and sp3d. Okay. And then which of the compounds have a square planar structure, and which of the compounds are polar? So let's take care of that while we go through. So this one's seesaw, and because of the lone pair, it is asymmetric, so it will be polar. Right, so there will be dipoles here, which won't exactly cancel because the structure would be pushed out of, well, not just because of that. If you add up the dipoles, they won't cancel, so it's polar. Here we've got minor dipoles between iodine and chlorine, and it will point towards the iodine. And again, it's asymmetric, so it will be polar. And the structure here is square pyramidal. Okay. Now this guy is trigonal, bipyramidal. Okay, and because of the perfect symmetry, this will be non-polar. Right, so far the first two have been polar, so this is the one that's non-polar. So this structure is square planar, and because of the symmetry, will be non-polar. And this one here is linear, and because of the symmetry, is non-polar. Okay, so which of the compounds are square planar? So for square planar, that was only KrCl4, and polar, that was the first two, and then the latter three were non-polar. Okay, so going through the solution given, this looks roughly like our structures. So TeCl4 and PCl5 should be roughly 120. KrCl4 and ICl5 should be sp3d2 hybridized. KrCl4 has a square planar structure. TeCl4 is polar, ICl5 is polar, while PCl5 is non. KrCl4 is non-polar, and XeCl2. So the only polars are these two, so that looks good. Let's say this is correct.